Welcome to session 6 of Digital Electronics Problem Solving class on IEEE. Last class we stopped at problem 20 in chapter 3 in the textbook Digital Design by Maurice Mano. There are a few more problems in this chapter. We'll skip the problems in chapter 3 for now, the remaining problems, and move on to chapter 4, and if time permits we'll come back to problems in chapter 3 later. So we'll start with chapter 4. Which is combinational logic. We'll start with problem 4.1. Consider the combinational circuit shown in figure P4.1, and this is the figure. There's input A, input B, input C, this is labeled as T1, this is labeled as T3, F1 is the output number 1, this T4, sorry, that's not T4, this is T2, and then that's given to an XOR gate. The output of that is T4. The other input of the XOR gate is D, and we have the second function F2. So this is the combinational circuit given. Part A, derive the Boolean expressions for T1 through T4, evaluate the outputs F1 and F2 as a function of the four inputs. T1 is the AND of B complement and C. T1 is B bar C. T2 is AND of A complement and B. So it's A bar B. T3 is the OR of T1 and A. So it's A plus T1, which is equal to A plus B bar C. T4 is the XOR of D and T2. It's D XOR T2, which is D T2 bar plus D bar T2, which is D into A plus B bar plus D bar A bar B, which is A bar B D bar plus AD plus B bar D. That's T1 through T4. To evaluate the outputs F1 and F2, we see that F1 is the OR of T3 and T4. So F1 is T3 or T4, which is A plus B bar C or A bar B D bar plus AD plus B bar D, and F2 is the OR of T2 and D complement, T2 plus D bar, which is nothing but A bar B plus D bar. That is part A. Let's go to part B. Part B is list the truth table with 16 binary combinations of the 4 input variables then list the binary values for T1 through T4 and outputs F1 and F2 in the table. So here is the truth table with 16 input combinations. We have the inputs A, B, C, D, then intermediary outputs T1, T2, T3 and T4, and final outputs F1 and F2. For 0, 0, you can verify this yourself. I'll give you the answer directly. You put the values of A, B, C and D in the formula for T1, T2, T3, T4 and F1, F2. And you'll end up with, and all the inputs are 0, only F2 is 1. For 0, 0, 0, 1, we'll get 0, 0, 0, 1, 1, 0. For 0, 0, 1, 0, we'll get 1, 0, 1, 0, 1, 1. You can check if C is so let's see. Um, Third input combination is 0, 0, 1, 0. A, B, and D are 0 and C is 1. If you see F1, A is 1, no, B is 0 and C is 1. So B bar C is 1. So F1 will be equal to 1. 1 plus, even if all the other terms are 0, since we are doing an OR operation, since B bar C is 1, F1 will be 1. And similarly, D is 0, so D bar is 1, D bar plus AB, A bar B will also be 1, so F2 is 1. In terms of T1 through T4, you can see T1 is B bar C, it is 0 bar 1, which is 1. T2 is A bar B, which is 0 bar 0, which is 0. T3 is A plus T1, since T1 is 1, T3 will be 1. T4 is D XOR T2, D XOR 0, which is D, and since D is 0, you will get 0 as the value for T4. In this way, you can find the value for all 16 combinations. I will not write down the remaining values. You can find them out yourself using the same logic. Finally, 1 1 1 1 input combination will give you 0 1 1 1 1 0. Part C, plot the output Boolean functions obtained in part B on maps and show that the simplified Boolean expressions are equivalent to the ones obtained in part A. So once you have the truth table, you can find out F1 and F2 as a sum of minterms. F1 is the sum of minterms 1, 2, 3, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15. F2 is the sum of minterms 0, 2, 4, 5, 6, 7, 8, 10, 12, 14. You can plot the K maps yourself using these minterms, and f1 will be equal to, using 4 variable k maps, you will get f1 is equal to a plus b d bar plus b bar d plus b bar c, and f2 is equal to a bar b plus d bar. So f2 in part A was a bar b plus d bar, that is matching with f2 in part that we got from simplifying the truth table in part B. f1 you have a plus b bar plus b bar d plus b bar c, but we have a plus b bar c plus ad plus b bar d plus a bar b d bar, so it's a little different and we will have to simplify this further. The function f1 is a plus b bar c plus a bar b d bar plus ad plus b bar d. This can be written as a plus ad can be written as a into 1 plus d, so we'll be left with only a plus b bar c plus a bar b d bar plus b bar d. Then you can group a and a bar b d bar and use the distributive law to write that as a plus a bar into a plus b d bar. We'll get a plus b d bar plus b bar d plus b bar c. So you can see that both using simplifying using k-map and directly writing it out in terms of t1 and t1 through t4 gave you the same expression. That is problem 4.1. 4.2. Obtain the simplified Boolean expressions for output f and g in terms of the input variables in the circuit of figure P4.2. There are two outputs f and g. and four inputs A, B, C and D. The simplified Boolean expressions for output f and g in terms of the input variables in the circuit of figure P4.2. So this is A complement, this is BC, this is A complement BC, A complement plus BC, this is A complement D whole complement. So this is A complement into A complement D whole complement, entire thing complemented. So f is equal to A complement and A complement D whole complement, entire thing complemented, and A complement plus BC. We have to simplify this further. We can write this as A plus A complement D and A complement plus BC, which will become ABC plus A complement D plus A complement BCD, which can be written further as ABC plus A complement D into 1 plus BC, which is nothing but 1. So you can write this as ABC plus A complement D, and the output G is equal to A complement D whole complement and A complement or BC, which is nothing but A plus D complement and A complement plus BC, which is ABC plus A complement D complement plus BCD complement. Using 4 variable K maps, the I won't be doing any of these K map simplifications in this chapter because we solved a lot of problems in the previous chapter that involved only K maps. So you can look at the recorded lecture of the previous live sessions for the simplification part. Using 4 variable K maps, the simplified expressions for f and g are: f is simply the thing that we got, there's no further simplification, but g can be simplified to be a bar d bar plus abc. The bcd bar part will vanish. For the circuit shown in figure 4.26, part A, write the Boolean functions Write the Boolean functions for the four outputs in terms of the input variables. And part B, if the circuit is described in a truth table, how many rows and columns would there be in the table? Let's see the figure first. This figure is given in section 4.11, figure 4.26. Let me go to the figure first. Okay. The figure is as follows. That's the first output, y0. Inputs a0, a1, a2, a3. y1, y2, y3, b0, b1, b2, b3, There's a select input S, that's complemented, so you get S bar, that is fed as the input to each of the first 4 AND gates, and then the third input of each of these AND gates is an enable input, which will enable or disable the circuit entirely. So these enable inputs will be connected to the second group of AND gates also, and the complement of S is connected to okay. Complement of S is connected as the second input to the second set of AND gates, which are connected to the inputs BI. So the question was, write the Boolean functions for the 4 outputs in terms of the input variables. And the solution to that is, you can see that if enable is 0, then all the outputs are simply 0, because the output of all the AND gates will become 0, because one of the inputs to the AND gates is uh, the complement of E. So if enable is 1, and then all of them will become 0. I made a mistake. Enable is active low here, so if enable is 1, then the output of all the AND gates is 0, and you will get 0 output. So enable has to be always 0 to get a proper output. So E complement will be one of the literals in the terms for the output. And whenever S is 0, S bar is 1, and here you have S bar or S complement, here you again have S. Whenever S is 0, the output of the final 4 AND gates is 0. The output of the first 4 AND gates is simply A0, A1, A2 and A3. So Y0, Y1, Y2, Y3 will be equal to A0, A1, A2, A3. When S is 1 S bar is 0 and S. So S bar is connected to the first 4 AND gates, so the outputs of all those AND gates will be 0. And so if S is 1, only the final 4 AND gates will give you a non-zero output depending on the inputs, and the first 4 AND gates will always be 0 when S is 1. So when S is 1, Y0, Y2, Y1, Y3 will be A0, Y1, Y2, Y3 will be B0, B1, B2, B3. And you can write this down as part A, Y0 is A0 S complement E complement plus B0 S E complement. Y1 is A1 S complement E complement plus B1 S E complement. Y2 is A2 S complement E complement plus B2 S E complement. Y3 is A3 S complement E complement plus B3 S E complement. Part B, for part B there are 10 inputs, 4 outputs. Inputs are A0 to A3, B0 to B3, S and E. Outputs are Y0 to Y3. Number of rows in the truth table is equal to 2 power number of inputs, is 2 power 10, so 1024 rows. Number of columns is the number of inputs, one column for each input, plus number of outputs, one column for each output. So 10 plus 4, 14 columns minimum. You can write intermediary output values as in some of the columns also, so you could have more columns than this, but if you are only writing the outputs and the inputs, then the number of columns will be 14. That was problem 4.3. Next is problem 4.4. Design a combinational circuit with 3 inputs and 1 output. Part A, the output is 1 when the binary value of the inputs is less than 3, the output is 0 otherwise. So the truth table will be as follows. Let us denote by the inputs by letters capital A, capital B and capital C, and the output by the letter capital F. Then 0 0 0 binary value is 0 is less than 3, so the output is 1. 0 0 1 binary value is 1, which is less than 3, so the output is 1. 0 1 0 binary value is 2, which is less than 3, so the output is 1. 0 1 1 is binary 3, so the output is 0. And 1 0 0 is 4, so 0. 1 0 1 is 5, so 0. 1 1 0 is 6, so 0. 1 1 1 is 7, so this is also 0. So that is the truth table for part A. So the function is f is, in terms of minterms, sigma of 0 1 and 2. We write the k map, get 1 1 1 here, a bar a, b bar c bar, b bar c, b c, b c bar, that is group 1, that is another pair. So you get f is equal to a complement b complement plus a complement c complement, or you can write this as a complement into b complement plus c complement. So you have b and c complemented using NOT gates, or together b complement plus c complement, and add with complement of a, and you will get f. That is the combinational circuit for this particular problem. For part B, we have the output is 1 when the binary value of the inputs is an even number. So the truth table would be 0 0 0 is 0, which is an even number. So output is 1. 0 0 1 is binary 1, which is an odd number, so output is 0. In this way, alternatively, you'll get 1 and 0, 4 is even, 5 is odd, 6 is even, 7 is odd. So this A bar A, B bar C bar, B bar C, B C, B C bar, this can be grouped into one quad, and the expression f would be F is equal to C bar. So you can see that if C is 0, the output is 1, and if C is 1, the output is 0. And that is true because an even number will have a 0 in the units place in binary number system, and an odd number will have a 1 in the units place in the binary number system. So if the LSB is 0, it is an even number. If the LSB is a 1, it is an odd number. So F is just C complement. Problem 4.5. Design a combinational circuit with three inputs X, Y, and Z, and three outputs A, B, and C, when the binary input is 0, 1, 2, or 3, the binary output is 1 greater than the input. Design a combinational circuit with three inputs X, Y, and Z and three outputs A, B, and C. When the binary input is 0, 1, 2, or 3, the binary output is 1 greater than the input. Okay. When the binary input is 4, 5, 6, or 7, the binary output is 2 less than the input. First, let's write down the truth table. X, Y, Z, A, B, C. Input combinations are 001, 000, 001, 010, 011, 100, 101, 110, and 111, 027. When the input combinations are 0, 1, 2, or 3, binary output is 1 greater than the input. So when it is 0, binary output is 1. When it is 1, binary output is 2. It is 2, binary output is 3. When it is 3, binary output is 4. When the inputs are 4, 5, 6, or 7, the binary output is 2 less than the input. So when it is 4, input is 4, output is 2. Input is 5, output is 3. Input is 6, output is 4. Input is 7, output is 5. That is the truth table for this particular function. So you can write from this A is sum of minterms 3, 6 and 7. B is the sum of minterms 1, 2, 4, 5. C is the sum of minterms 0, 2, 5, 7. And you can simplify using K-maps. You will get A is xy plus yz. B is xy complement plus y complement z plus x complement yz complement. C is xz plus s complement z complement. And the circuit for this is as follows. We have xy and z. Xy plus yz is output A. You can get y complement x, y complement z, and x complement y, z complement. Or of those is B. Now C is xz plus x complement z complement. So you can get xz x complement z complement, and the sum of those is C. That's problem 4.5. We are halfway through the session, so I'll take a 5-minute break and go get some coffee in the meantime.